Greetings, traveler. I'm the calculus cleric, and today we're working with Taylor polynomials. So the specific problem is to compute the Taylor polynomial indicated and apply the error bound to the indicated value. And below they give us that f of x is equal to cosine of x, a is equal to 0, and the absolute value of cosine 0.25 minus the Taylor polynomial taken to the fifth degree of 0.25 absolute value. Okay, so for those of you that don't know what this is the indicated value for the error bound section. We'll get to that later. So there are two parts to this. One is compute the Taylor polynomial indicated, and the second one is to apply the error bound. So let's take this linearly and first compute the Taylor polynomial. So they give us the function they want us to compute the Taylor polynomial of. And basically what we're going to do is we're basically going to take the function itself and then take all of its derivatives and then add them all together. You'll learn how to sum this up to infinity when you do Taylor series, but not when you do Taylor polynomials. Okay, so first they give us f of x is equal to cosine of x. And what this a equals 0 is that it's telling us where to start at. So the function only defines the coefficient in front of the Taylor polynomial. There's a bunch of stuff, some stuff after it, but we can get into that later as well. And basically what we do to find the coefficient is we plug the a value into the x. So they give us a equals 0, so we just plug 0 into x. And cosine of 0, which is equal to 1. And then we simply take the derivative of f of x, and then we plug into 0 into that as well. Negative sine of 0 is just 0. And then we take the derivative of that. And as you can see, we keep taking derivatives over and over and over again until we hit the wanted degree, which in this case is 5. So we're going to do this all till we reach the fifth derivative of f of x. However, we're going to have to take the error bound, so we're going to have to go out to the sixth derivative. I'll explain why later. But let's do this first. And derivative of sine is just cosine, so negative cosine x, plug in 0 once again. Negative cosine of 0 is just negative 1. Third derivative. Derivative of cosine x is negative sine of x. Plug in a 0. Sine of 0 is 0. Fourth derivative. Derivative of sine is cosine. Plug in 0. Cosine of 0 is 1. Take the derivative one more time, and then one more time after that. Derivative of cosine x is negative sine of x. Negative sine of 0 is 0. And the sixth derivative. Derivative of sine of x is cosine of x. Plug in a 0. Okay, so this is a repeating pattern, but we're done with that. Okay, and now we have to add in all these stuff afterwards, which is actually a lot simpler than you think it is. So t of 5 of x, we put an x there because we're not going to plug in a specific value in for x. And then we start with the first coefficient, which is just 1. And we just leave that as it is. And then we go on to the next coefficient, which is 0. And then what comes after is x minus a to the first degree, and then all over the 1 factorial. So we're going to keep adding onto this. Look at it in general terms, it looks like this. But because this is our first degree, because it's our first derivative. Then we're going to put a 1 into the ends. And the reason why this is just 1 with nothing after it, because this was like our 0th term. So when we plug in 0 onto the top, that's just 1. We plug in 0 onto the bottom, it's just 1. So there's no x's afterward. But because our a is 0, that makes it really easy for us. There's going to be nothing there because x minus 0 is just x. And we call this kind of polynomial a Maclaurin polynomial. And I'm just going to replace the ends with the 1s. Actually, I don't even need to replace the ends with the 1s. You just get 0x all over 1 factorial. I like to write 1 factorial because it reminds me that there's something there for the next step. And the next coefficient is -1. We just write that down, plop it in front. And then just x minus 0, we can forget about that. And then we just add 1 because this is the now second derivative. So it's x squared all over 2 factorial. And then we keep doing this all until we reach 5. And if you can remember, it's actually okay to skip the ones with the 0 as coefficients in front of it because 0 multiplied by anything is 0, so we don't need them. But you might want to write that down in case you want to keep track of what degree it is. And then 1 x to the 4 all over 4 factorial. And then fifth, 0. Actually, I'm not even going to write that down because it's 0 and there's nothing you keep track of afterwards. So I'm going to go clean this up and get rid of these 0 terms. So it's 1 negative x squared all over 2 factorial plus x to the 4th power all over 4 factorial. And that is our Taylor polynomial when we take it out to the 5th degree. Although in actuality, we can actually simplify this a little bit more by solving out the factorials. So 1 minus x squared over 2, because it's 2 times 1, the 2 factorial, so it's just 2, plus x to the 4th power all over, so 4 by 3 by 2 by 1, which is 4, 3, 12, and then 12 by 2 is 24. So 4 factorial is equal to 24. And that is our final answer for part 1 when it's all simplified. Okay, so now we move on to part 2, apply the error bound. Okay, so the formula for the error bound of a Taylor polynomial is f of x minus t of n multiplied to the x. So that's that thing over there that we saw is less than or equal to k x minus a to the n plus 1 all over n plus 1 factorial. And the reason why we took it out to the 6th derivative was because k is greater than or equal to the absolute value of f of n plus 1 of u. And our n plus 1 is going to be equal to 6 because we're taking this out to the 5th polynomial. So that's why I had to solve for the 6th derivative. And so they want us to find the maximum value of this function over here. And it's an absolute value, so we don't have to worry about positives or negatives. U just represents some variable where the function is at its maximum. And as you can see, k can also be bigger than the maximum value of f of n plus 1. So really, we can set k to anything we want, but the problem is the bigger we set k, the bigger our error is going to be. But since the function is negative cosine of x, it's relatively easy to find the maximum of that. We know that the maximum of a cosine function is 1, and it's because it's harmonic and it's just going to oscillate between 1 and -1. But because it's absolute value, we don't have to worry about that -1, we just worry about that 1. So our k, we're going to set that equal to 1, and that makes it really easy on our calculations, to be honest. And we're going to start plugging things into the formula. So cosine of 0.25 minus t fifths is 0.25 is less than or equal to, and it's less than or equal to because, as I said earlier, the k can honestly be anything that's super large. So it can actually be larger than the error of this put together when we subtract those and it gives us a result. The error that we find using the formula can actually be much larger than the result if we just take this out and find the difference. So k, which is just 1, and then x negative a. So our x value is 0.25. X is the value that you're trying to find the error of. So what our Taylor polynomial is doing is it's like approximating the value of 0.25 of the function f of x, and we're trying to figure out how accurate that's going to be. So we just plug in 0.25 into x, and then we subtract that from the a value, which is 0, and then we take that out to the exponent of n plus 1. So our n is 5 plus 1, that's going to be equal to 6. But I'm just going to leave that as is now. And then the bottom is the same, n plus 1 factorial, which is 5 plus 1 is going to be 6 as well. And then let me write that out again. So 0.25 to the 6 all over 6 factorial. I can delete the 1. Now, if you want to find the decimal equivalent of this, you can take out your calculator and solve this out. And after solving that, you're going to get a really small error. So I got about approximately 0.000000339. And that is the final error.